Hello. In this video, I'm going to be solving problem 55 from section 13.1 of James Stewart's Calculus Early Transcendentals. The problem reads, try to sketch by hand the curve of intersection of the circular cylinder x squared plus y squared equals 4 and the parabolic cylinder z equals x squared. Then, we need to find parametric equations for this curve and use these equations in the computer to graph the curve. So first for the sketch, I've already sketched this ahead of time. And so I'm going to jump to the sketch right now and show how you might come about this sketch on your own. So if I swipe over here, I get this sketch right here. And as you can see, this U-shaped surface, this is supposed to indicate my equation, what is it? Z equals x squared. And the reason it looks like this is because at least on the xz plane, and note here that my positive x-axis is this way, and my positive y-axis is this way. If I were to plot this surface in blue on just the xz plane, where again, I'm going to be consistent with my sketch here and make the positive x-axis to the left. The surface would look like, well, it would just look like this parabola here. It's the graph of the equation z equals x squared. But because this equation does not depend on y, we're going to get the same cross-section no matter which plane we slice this surface about, provided that our plane is perpendicular to the y-axis. And so we get just this parabola, but just kind of, what would the word be? Swept out along the y-axis. Similarly, this surface right here in the inside is meant to represent our cylinder x squared plus y squared equals 4. And the reason it looks like this is because, if you draw the projection of this surface onto the xy plane, and here I'm going to be a bit different. I'm going to let this be the positive x-axis, this be the positive y-axis. Then the projection of our surface would just be the circle with equation x squared plus y squared equals 4. And again, because the equation does not depend on z, we're going to get the same shape no matter which cross-section we take, provided our plane is perpendicular to the z-axis now. And so we get a family of circles, but they get swept out along the z-axis. To sketch the intersection is a bit more difficult because, well, we're limited by our own drawing abilities, but roughly this line right here is meant to indicate where the surface would intersect our cylinder. And you can kind of think of it as just kind of cutting into the cylinder and cutting out a Pringle shape. It's not apparent here from the sketch I've given, but it's going to become clear, like the shape looks like a Pringle if we go to the computer, as the problem asks us to do later. But yeah, this is the sketch that we would want to give if this were like a homework problem. But okay, now let's get into the meat of this problem, which is to actually find parametric equations for this curve. And how do we do this? Well, I see this equation, and the first thing that jumps to my eye is that this is a circle. Technically, in the XYZ space, this represents a cylinder, as we've seen with my sketch. But at least if we project this down into the XY plane, we're going to get a circle of radius r equal to 2. And its equation will be x squared plus y squared equals, well, in this case, 2 squared, which is the same as 4. So, because this is a circle, already my mind jumps to the familiar parametric equations we know for circles, which let me remind everyone. The parametric equations for a circle centered at the origin. So its equation is going to be x squared plus y squared equals r squared. These equations are x is equal to r cosine theta, y is equal to r sine theta, and here our parameter theta varies from 0 to 2 pi. It actually doesn't matter what this parameter interval is, just so long as it has a length of 2 pi, but this is the typical one, and this is the one we'll use. Okay, so from this information, because the projection of our cylinder onto the xy plane is this perfect circle, if we choose to use this parametric equation, then if we choose to use these parametric equations, then in 3D, the parametric equations will still be x is equal to, well, here r is 2, so this will be 2 cosine theta. Y will be 2 sine theta. And all that's left is an equation for z. But remember that we are intersecting the parabolic cylinder given by the equation z equals x squared. So if x is equal to 2 cosine theta, then z is going to be, well, we just plug in whatever x is, which in this case is 2 cosine theta. And if we simplify, we get 4 cosine squared theta. And so just to clean things up, our parametric equations are going to be x is 2 cosine theta, y is 2 sine theta, and z is 4 cosine theta, cosine squared theta. And our interval for the parameter theta will go from 0 to 2 pi. What if we wanted this parameterization in vector form? Well, remember, and here actually, let's switch the parameter to t, just to be consistent with our book's typical choice for the parameter, which is t. Recall that our the corresponding vector equation in general will be the x components, the y components, and then the z components. Well, where here, these are the parametric equations we have up here. And to emphasize that, we might even add these parentheses with t's here to emphasize that these are functions of t. And all we need to do is plug these in to our vector to get the corresponding vector equation. And this gives us two different ways to express the parameterization of the intersection of our two surfaces. Okay, that completes the solution for finding the equations. Now let's turn over to Desmos 3D and see what this intersection looks like graphically. Okay, welcome back. So here I am in Desmos 3D, and I've prepared my equations off to the left, as you can see, and I'm going to plot them one by one and see what they look like. So first, let's go ahead and plot our cylinder. And as you can see, we get the cylinder as expected. And here, if I orient my axes so that they're consistent with my sketch from earlier, so that the positive x-axis points in the left, then if I plot z equals x squared, it looks just like we expect. It stretches out along the y-axis, and at each plane perpendicular to the y-axis, we just get a parabola, which we can see if we just fix it right here, and then remove the cylinder from the picture. Finally, let's draw the intersection of the two surfaces, which is the last item on my Desmos graph. Turning it on, we can see this green curve form around where the two surfaces intersect. And you might notice how in the sketch, the curve actually goes from the XY plane up to some higher points Z coordinate wise. And this should make sense because if you look at the last components of our parametric equation right here, which is 4 cosine squared t, well, that oscillates between 0 and 1, or 0 and 4, sorry, because cosine squared oscillates between 0 and 1. And in fact, just because the maximum of cosine squared is equal to 1, we can see that these maxima, the highest points of our curve, are going to occur at the z-coordinate z equals 4, and we can see that from the graph right here too. Okay, this completes the solution of problem 55. If anybody has any questions, please feel free to leave a comment down below. Otherwise, I will see you all in the next video.